Alright, so this is lecture 15 on partial differentiation with 3 or more variables and applications. This is page 170 to 179 in the lecture notes from 2020, give or take. This should be a relatively quick lecture because essentially we're just doing what we did already, except instead of having 2 variables, we might have 3 or more. Alright. Of course, the geometry here is a little bit different as we think about the geometric interpretation of these things. All right, like how do you visualize a function of 3 variables exactly anyway, right? I mean, think about that just for a second before I do anything else. If I think about f of xy, right, I can visualize a function of 2 variables by thinking of z equals to f of xy, right? And so then, you know, I can think, oh well, it's some kind of surface, right? So I can do that, right? And I can think about, the domain of f kind of being down here or something, right? I can think of the domain of f as being somewhere in the xy plane, and kind of the function just maps up to there, something like that, right? But if I've got a function of x, y, and z, right? If I was to set that equal to another label, another letter w, I can't visualize that directly because I need 4 dimensions, right? So we have other ways of visualizing functions, right? Besides looking at their graph, we can look at their level curve in the, so we just talked about in the previous lecture, right? So for a function of 2 variables, we can set this equal to a constant, and that will give us level curves, right? Of course, we have 2 options for functions of 2 variables. We can either look at level curves to understand how the function's behaving, or we can look at the graph to understand how the function's behaving. For functions of 3 variables, though, the graph is in 4 dimensions. That's kind of tough. So if we set this equal to a constant, it turns out if you've got 3 things and you set equal to a constant, it basically leaves you with 2 things left over usually, and this will define not a level curve, but a level surface, right? For example, if this function is x squared plus y squared plus z squared, and we set that equal to a constant, then the level surface is a sphere, right? So we have that. The geometric understanding of functions of more variables, we're more limited. When we have 2 variables, well, that's a very special place. We can either look at the graph or we can look at level curves. For 3 variables, if you want direct visualization, you kind of are forced to look at level surfaces, all right? Okay, so with that little bit of situational awareness behind us, here's the definition of partial derivatives in 3 dimensions or more dimensions. 3 dimensions to start with. So the derivative with respect to x, y with respect to z, we define in terms of directional derivative in the x hat, y hat, or z hat direction, respectively. And there you go. So that's how we differentiate with respect to x, y, and z. We use directional derivatives. Now, okay, that you're like, well, I don't really understand the directional derivative, so you're just defining something I don't know in terms of something I also don't know. That's not really useful to me. Fair enough. So here's a more explicit and explicit definition and a little bit of intuition. All right, so natural interpretations for these partial derivatives. F sub x, which, remember, the same notation again. F sub x is partial f partial x. Likewise, f sub y is partial f partial y. F sub z, that's the new one, is partial f partial z. Notice here that x, y, and z are like all independent in this context. Previously, our use of z was as z equals f of xy. That means our previous usage of z in the previous lecture, z was a dependent variable. So dependent versus independent is an important distinction to be aware of. Now I'll tell you explicitly what that means in terms of partial derivatives here very soon. But before I do that, here's the definition of how we differentiate with respect to x, y, or z. We simply let the x vary, hold y and z fixed. We let the y vary, we hold x and z fixed. We let the z vary, we hold x and y fixed. That's how we differentiate with respect to x, y, and z respectively. And it's really just an ordinary derivative where we treat the other variables like constants. So it's not a big deal. You know how to do this already, I think. And the properties, I hope, are not surprising. So, here's the properties. Just like we had for two variables, we have linearity, we can pull out constants, we have product rules, whether you're using the x, y, or z derivatives. We got a chain rule, and, let's see here. That was supposed to be R3 right there, folks. Oh, wait a minute, no. No, h is excuse me. H is a function on R. I'm composing f with h, so it's h composed with f. Let me tell you the story there. H composed with f. F is starting with R. We go from R3 to R to R again. So this is the f, and this is the h. I mean, technically it's a subset of R3 because f could have a domain, which is anyway. And so I won't show you the proofs of those things. Oh, but I should, unfortunately, well, I don't know if it's unfortunate or not. This right here, I should unwrap a little bit. What does that mean? Let me write it on my page that I'm planning to scan for you guys over here. So partial x sub I partial x sub j. Right, I said that's equal to Kronecker delta ij. What that means is it's 1 if I equals to j. It's 0 if I is not equal to j. So in the other notation, this is like partial x is 1, partial x partial y is 0, partial x partial z is 0, partial, let's see here, x partial z, excuse me, I want to do the y. Partial y partial x is 0, partial y is 1, partial y partial z 0. Alright, I've done this much. I guess I should finish. Partial z partial x is 0, partial z partial y 0, partial z 1, right? So these 9 derivatives are all captured by this formula where I and j, 1 less than or equal to I comma j less than or equal to 3. The thing is, this is true. This relation for partial derivatives is true if we look at a function. If we look at a function of n variables, if you looked at a function of x1, x2, xn like that, we could do that next, and then you can define partial derivatives of such functions. In that context, it's still the case that partial xi, partial xj is equal to Kronecker delta ij. It's just then it includes like n squared of these equations. See, it's got 9. This has 9 of these equations. This would be n squared in that context. Anyway, let me stop with my over enthusiasm about index notation. Here's some examples. Here we go. So if we have g of xyz equal to let's see, I can zoom in a little bit more. Whoop, oh, whoop, whoop. Too far. There we go. And now I just gotta remember to zoom out when I'm done, right? So the derivative of xy squared z cubed sine of xyz. So differentiate with respect to x, it just kills the x and leaves y squared z cubed, right? That first term. When we differentiate with respect to y, we get the 2y, but the x remains, right? When you differentiate with respect to z, you get the 3z squared, and the xy squared stays. Now, when we differentiate sine of xyz, every time we get cosine, cosine, cosine of xyz, because that's, it's a composite function. So the chain rule says, like, partial partial x of sine xyz is equal to cosine of xyz. See, I've already regretting my greedy close-in zoom. There we go. Cosine of xyz, partial partial x of xyz, which is, this differentiates to just y times z. So we get yz cosine of xyz. And by almost the same pattern, we pick up xz and xy for the y and z derivatives, whereas we got yz for the x derivative. So there's an example. We can also talk about evaluating the derivative at a point, like here. So calculate x over y plus z, calculate partial f partial z at the 3, 2, 1 point. So let's see here. First of all, I just calculate the derivative. It's got a reciprocal function, so that gives me minus 1 over the thing squared. And then by the chain rule, I have to multiply by the derivative of, with respect to z, of the thing in the denominator, which is y plus z. That x is just riding along. And of course that gives us 1, so we just get this minus x for y plus z squared. And then if we're calculating the derivative at 3, 2, 1, we put x equal to 3, right? Y equal to 2, and z equal to 1. So we get a minus 3 over 3 squared, which is minus 1/3. Okay, great. Here's a pretty neat calculation. If we take the partial derivative of the distance from the origin function, this is nothing more than the rho, right? This r is equal to rho usually. Usually we set a rho equal to square root of x squared plus y squared plus z squared. Like usually rho. So sometimes I write r here, and that's a holdover from my physics background. In physics, we like to use r for where we use rho in math. Anyway, partial r partial x is x over r here as you work it out. So we get the chain rule, and then we have to differentiate the inside function, which gives us a 2x. The 2's cancel, and that's r again, so we get x over r. And, symmetrically, we can find partial derivative of the, radius function. The spherical radius function is y over r with respect to y, and z over r with respect to z. And, in fact, you can easily extend that example to n dimensions. And in n dimensions, that example, the distance from the origin in n dimensions is given by u equal to square root of the sums of the squares of all the variables. And if you calculate the derivative of that with respect to the jth variable, you get 1 over twice, u times that partial derivative, which just gives us 2xj, so we get xj over u. And in other words, the partial derivative of r with respect to xj is xj over r for the sphere, for the radius in n dimensions. That's kind of cool. This one's a little bit tougher. This is an example of a partial differential equation. You may or may not know this, but most of the important equations of physics are partial differential equations. For example, Laplace's equation is, well, we'll describe that more as we go on this semester. That's like one of our goals, is to understand the language of classical mathematical physics. And Laplace's equation is a big part of that, but I'll just state it for now. Laplace's equation is that uxx plus uyy plus uzz equal to 0. And I'm claiming that 1 over the square root of x squared plus y squared plus z squared is a solution to that, right? Now, we just proved that the derivative of u, this is 1 over, well, I'm sorry, u is 1 over r, so we know that partial r partial x is x over r. and partial r partial y is y over r, and partial r partial z is z over r from a previous example. And so if we let u equal to 1 over r, which is what I'm claiming is a solution, then we have to do the chain rule, minus 1 over r squared, but then we have partial r partial xj, which by the way is just xj over r. So we get minus xj over r cubed for partial u partial xj. And then of course I have to calculate the second derivative. And the second derivative gives me partial derivative of minus xj over r cubed, which by the chain rule, by the product rule, I get a minus 1 over r cubed, because the derivative of that with respect to that's just 1. And then I get a 3 over r to the fourth, and then this is going to give me xj over r again, so I get r to the fifth over here, minus 1 over r cubed plus 3x squared x sub j over r to the fifth. And so if you collect terms and go back to the other notation, you've got that uxx plus uyy plus uzz is minus 3 over r cubed plus 3 times x squared plus y squared plus z squared. But if you make a common denominator, you've got, this is 0, because if you look at it, I guess I'm thinking of it in terms of canceling. So if you cancel that, you get minus 3 over r cubed plus 3 over r cubed, so it's 0. Woohoo! All right, so there's some examples of partial derivatives of 3 or more variables. It's not really much different than what we've already done. The definition of continuously differentiable that I talked about for 2 variables, we can also talk about for n variables. A function is said to be smooth if it has partial derivatives of all orders and they're all continuous. So C infinity function is sometimes called. The formula for the directional derivative in that context, if you have a continuously differentiable function, then the directional derivative you can get from the gradient dotted with the unit vector in question, just like we did before for 2 dimensions. We still can do it in n dimensions. And the proof, again, is delayed. So in short, the gradient vector field is now a vector field for a function of n variables. The gradient vector field is an n-dimensional vector field. We visualize, sorry, I'll put it back in frame. For a function of n variables, the gradient vector field we visualize in the domain of the vector field. It's also a vector field in Rn. And so what I'm saying is we attach, at each point in the domain for which all these derivatives exist, we think about attaching that vector and pointing in that direction, and it describes how the function increases and decreases at that point. Even in n dimensions, we still have that the directional derivative is the magnitude of the gradient times the cosine of the angle between them. That's still good in 2 or 3 or however many dimensions you got. Here's an example. But however, the word problems get trickier, guys. Watch out for these. Watch out for these. So check this out. Here's a good example on how it's more subtle. There are still reasonable questions I can ask. I just have to be careful not to ask. There's some questions that I can ask in the plane that I can't in good conscience ask for functions of 3 or more variables. Let me show you what I mean. So look at a function of 3 variables, x squared plus y squared plus z squared. My question is simple enough. Does f increase at a rate of 10 in any direction at the point 1, 2, 3? Seems like a innocent enough question. When we asked that for 2 variables, we could solve it. We did that at the end of the last one of the previous lectures, and we saw that we end up just needing to find 2 directions in which it could happen. And so here, well, let's get started. We calculate the gradient, 2x, 2y, 2z. We evaluate at the point 1, 2, 3. We get 2, 4, 6. The magnitude of the gradient is the length of that vector, which is square root of 56. That's going to be the maximum rate possible. Therefore, the answer is no. Does it increase at a rate of 10 anywhere? Well, square root of 56 is less than 10, so no. This function, in fact, increases at a rate of 56 in the direction of root 1 over root 14, 1, 2, 3. Okay, great. But let's see, let's make it more interesting. So that's an easy question, actually. This is a fair test question. What if instead of saying 10, I said 4, All right. So that's, well, see here if I've got room. I think that's gonna, let me say I'm gonna, so if we traded 10 for 4, the question is what would happen, right? So the next problem actually has that kind of pattern, so let's go to the next problem. So here we've got f of x, y, z equal to 2x plus y plus 2z. Does f increase at a rate of 2 in any direction at the point 1, 1, 1? So this time the gradient vector is just a constant vector, 2, 1, 2. And the magnitude is root 9, which is 3. That's the maximum rate. So can we attain 2? Yep, yes we can. So how do we find the direction in which that occurs? Well, we need to solve that the directional derivative at 1, 1, 1 in the ABC direction, 212.abc, is 2a plus b plus 2c equals to 2. Okay, but this is for a unit vector, right? The unit vector condition is a squared plus b squared plus c squared equal to 1. So, okay, great. Well, we can eliminate c. We can solve this equation for c and substitute in. And there you go, a squared plus b squared plus 1/4 of that equals to 1. And that's actually kind of the solution. Any choice of a and b which solves this equation will produce a, and then you choose c like so, that will give you a direction at the point 1, 1, 1, where this function is increasing at a rate of 2. In other words, the solution is an ellipse in AB space. There's not just one direction. And if you looked at ABC space, it's some kind of ellipse, or I think it may be a circle on the sphere. I'm not, well. Anyway, there are infinitely many directions where it increases at rate 2. And so here I find a couple of them by plugging in things. So, 0, 0, 1, 0, 4/5, 3/5. Those are a couple of example directions in which the point where f increases at rate 2 at the 1, 1, 1 point. But there's infinitely many answers. There's not just 2 answers like there was for function 2 variables. All right. So, I mean, essentially the problem is just this: when you have more than 3 or more variables, when you have 3 or more variables. So let me just contrast the situation here, guys. So if we have like directional derivative u hat direction of f at a point equals to some constant, right? So this is the problem. N equals to 2, we've got something like equation for AB, right? And we also have a squared plus b squared equal to 1. We have to solve those simultaneously. But for n equals to 3, the directional derivative is going to give us some sort of equation for AB. And I think that equation has to be linear, actually. So like ABC rather, right? So n equals 2, we have the unit vector as AB. That's the main point here. N equals 3, the unit vector we're looking for is ABC. And now it's going to satisfy a squared plus b squared plus c squared equal to 1. So, when you look at a linear equation in ABC, that's like a plane. So the answer here is something like the intersection of a plane with a sphere, whereas over here the answer is like a line intersecting with a circle. So line through circle, easy enough. Sphere with a plane, it's more complicated. You can do them, but it's just you have infinitely many answers. So if I wanted to get a specific answer to a question like this, I would have to restrict it further. I'd have to give a more refined question than just find the directions in which the function's increasing at a rate. All right, so let's see here. Let f of x, y, z equal to this function. Find the rate of change of f at 0, 0, 0 in the 5, 1, minus 2 direction. So first of all, don't fall for the trap. First of all, you have to find a unit vector in the direction so we can calculate the directional derivative. So that vector has length 30. So we normalize 1 over root 30. There's our handy-dandy unit vector. The gradient we calculate is this. And so that tells us that nabla f of 0, 0, 0 is 1, 1, 1. The exponential of 0 is 1. But z, x, and y are all 0 at 0, 0, 0, so those terms drop out. Anyway, we get gradient vector field is 1, 1, 1 at the point 0, 0, so we have to do the unit vector, the v hat dot with the gradient, and lo and behold, we get 4 over root 30, and that's it. It's just, it can be, you know, as simple as that. It doesn't have to be complicated here, right? Sorry if I was out of frame just now. I should leave it big or something. Let me stop and check my framing before I say anything else. Okay, so this one here, this one is the function x over y plus z. So I say find the directional derivative at the point 4, 1, 1 in the 1, 2, 3 direction. So I have to normalize my my vector has length 14, root 14, so I divide by root 14. There's my unit vector. I calculate the gradient. I plug in the point, right? So that I have the gradient at the point. I take the dot product with the unit vector, and that gives me the rate of change. So, you know, basically 3 steps. Step 1, find your unit vector. Step 2, calculate your gradient, and plug in the point, and then, maybe there's 4 steps. Find your unit vector, calculate the gradient, evaluate the gradient at the point in question, and then take the dot product with the unit vector and the gradient vector. And then that'll tell you the rate of change. All right. And then, of course, there's conceptual questions that we can tack on here, like let f of xyz be 5 times square root of x plus y squared plus z squared. Find the maximum rate of change at 3, 6, minus 2, and determine the direction in which it occurs. So, all right, great. We calculate the gradient, and it's easy enough to check that it's going to give us 5 over r xyz. In fact, that's a consequence of differentiation we did earlier, because we already proved like partial x is like x over r and so forth, right? So I'm just basically saying, hey, you can check that that's true again. Anyway, there it is, and then plug in 3, 6, minus 2, and we get 5 sevenths, 5 over 7. Why 7? Is that 7? 9 plus 36 is 45. 45 plus 4 is 49. The square root of 49 is 7. Yes, yay! So r is 7. 5 sevenths, 3, 6, minus 2. And so if we calculate the length of the gradient vector, we get 5. And so the maximum rate of change is 5, right? And the direction in which it occurs is in the gradient vector direction, right? So we just let u hat actually be 3, 6, minus 2 again. The reason for that, of course, is that this is the gradient points in the radial direction. So, but anyway, there it is. So, so this is like, more generally, that's the answer for different choices of theta. When theta equals 0, we get rate 5. And if you want the angle between u hat and the gradient vector to be 0, you want u hat to point in the direction of the gradient vector, which, remember, we already found was 3, 6, minus 2. So 3, 6, minus 2 divided by 7 is a unit vector in that direction. All right, moving along here. So here is yet another directional derivative example, which I'll let you read. I think we've done enough of them. All right. So what is a critical point? For a function of many variables, we say p naught is a critical point if the gradient of p naught does not exist or it's 0. So, sorry, let's try that again, but in frame. Let me zoom out a bit so I stop getting myself into trouble. There we go. or stop getting myself into so much trouble. So the gradient is if when the gradient's 0, that's a critical point, right? Or if the gradient doesn't exist, that could be a critical point, just like in Calc 1 with derivative. So let's see here. So these are some comments. Like if you go back and look at the examples, we can see critical points for some of the examples. But anyway, we'll come back to say more about critical points in a future lecture when we talk about optimization. Although we can see some of that as we look at gradient vector fields. So what's a gradient vector field? So for a gradient vector field, we just imagine attaching the gradient vector at each point in the domain of the function. We already did it for 2 dimensions, but for 3 dimensions, our domain is 3-dimensional, right? So when we think about the gradient vector field for a 3-dimensional function, or rather a function with a 3-dimensional domain, then we're talking about assigning a vector to each point in 3-dimensional space. Now that's harder to draw pictures of, but thankfully I have some software that has done some nice pictures for me. And what these pictures have are both they have level surfaces for the functions in question, as well as the gradient vector fields. And so you can kind of see how they work. Let's see here. Zoom in a bit. So here I have the coordinate functions x, y, and z. The gradient is x hat, y hat, z hat actually respectively. And here's some pictures. So these are actually going to be constant vector fields. And the level surfaces are planes, right? And the direction vectors point normal to the plane, basically. I think this is x hat. I think this is y hat. And if I had to bet, I would say next page we'll have z hat. There it is. And oh, and also, so z hat, the z hat points up. These are level surfaces. Z equals to a constant, you know. And here I foolishly tried to plot the direction vectors for both x hat, y hat, and z hat all at once. If you look, and you get, I mean, if you get this out and look at the PDF, maybe you could zoom in, and you could see that the x hat, the y hat, and the z hat meet, and they make like little right-handed triples. Try that again. Oh, it's too big. Maybe I can. I will have my right-handed triple. Haha, like this. Right, little right-handed triples like that. No. Sorry, I should stop. And close my markers back up. I don't want them to dry out. Anyway, so this is a picture of the unit vector fields for both x hat, y hat, and z hat. And I would just point out, we can calculate the unit vector fields for coordinates in n dimensions just the same by calculating gradients and normalizing them. So, for example, cylindrical coordinates, r hat, theta hat, z hat, all right. We really went through that calculation before in the n equals 2. But now this one, well, here's the picture of them first, I guess I should say. This is a picture of r hat, the spherical radius. Here's a picture of theta hat. It wraps around the z-axis. And then, of course, here's a picture of z hat. It just points up radially. And then this is a picture which has all 3 on it at once. And if you look carefully, you can see that z hat, theta hat, and r hat, wherever they're attached to a point, they form a right-handed triple. Now, next up, the spherical coordinate system. If we calculate the gradient for this function, for that function, for that function, and we normalize it, in other words, gradient of rho divided by length of rho, gradient of phi divided by length of phi, length of the gradient of phi, gradient of theta divided by the length of the gradient of theta, and you do the calculation, you'll get exactly the formulas we wrote before. And so I have the rho calculation here. I think I leave the other 2 for your homework, but I would just like to point out that we have a method for deriving the spherical frame now, and that's kind of neat. And I also have a picture of it to share with you. So this is the rho hat, the spherically outward frame. This guy is the theta hat, so it's like always wrapping around in the standard angle direction. And this one over here, this is a phi hat. It kind of looks like a Death Star or something, doesn't it? But it points in the direction of increasing phi, which sweeps down off the z-axis. And then over here, for a quarter, for one quadrant, I think the first quadrant, or well, first octant maybe. I don't know how to number them. Here we're looking at the. Man, I said this video was going to be short. That was wrong. These are, again, from right-handed triple. If we look at rho hat, phi hat, and theta hat, you can see that they're meeting at right angles. But you can also see that the way they're assigned is quite complicated in contrast to, say, the Cartesian or the spherical coordinate or the cylindrical coordinate system. But anyway, the larger point here I would point out is that the gradient vector field, nabla f, is normal to the level surface f of x, y, z equal to k. And, again, I'll offer a proof with calculus later. This example is, again, a physical example. I look at the voltage as a function of 3 variables. Those are pluses. And you calculate that's the voltage for a point charge. You calculate the gradient of it, and you get the Coulomb field, which is in the radial direction, and depends on the squared distance from the origin. This is like, the usual Coulomb field if you studied it in electrostatics. And here's a picture of the ellipsoid. Here's some ellipsoid curve. So like if you set x squared over a squared plus y squared over b squared plus z squared over c squared equal to a constant, you calculate the gradient vector field. It looks like that. And here's actually a picture of some of those ellipsoids and the gradient vector field, how it points radially outward from those level surfaces. So it's very neat. We have a way to now notice what's happened is now when we think about a level surface, we can talk about the normal direction to a level surface, even if it's curved. Right up to this point, we could talk about the normal to a plane. We now have the technology to talk about the normal to a curved surface, and so we will talk about that more in a future lecture. So I'm going to stop it here. Thanks, guys.